We're now going to come back and consider inclined planes again. So we're now going to consider inclined planes with an energy approach. So previously we've looked at inclined planes and we've considered all the forces acting, and we've applied our equations of motion to work out things such as the speed and the acceleration of an object on an inclined plane. Now we can actually get the speed and the displacement and things of an object on an inclined plane also using an energy approach. So both these force and energy approaches are equally valid. In some situations it'll be faster to use the forces approach, in some situations it'll be faster to use the energy approach, but both should end up with the same answer. If you practice a lot, then you'll be able to tell, possibly for most questions, which way is faster. Generally, if you need to calculate an acceleration, the forces way can be faster. If you're only looking at speeds, then possibly the energy method is faster. So for the case with no friction, so for example a cart rolling down an inclined plane for which the friction is pretty much negligible, then we can use our rule that mechanical energy is conserved, as there are no non-conservative forces doing work in this case. So in this case, the initial potential energy plus the initial kinetic energy, so that's Ui plus Ki, is equal to the final potential energy plus the final kinetic energy, Uf plus Kf. Now in the case where friction is involved, so for example a box sliding down or up an inclined plane, in this case our initial energy is equal to our final energy plus the work done overcoming friction. So the work done overcoming friction is effectively energy which is lost from the system. So we can write that EI is equal to W plus EF, where EI stands for the mechanical energy. So this is the initial mechanical energy, so that's Ui plus Ki, and EF is the final mechanical energy, UF plus Kf. So remember, W in this equation is the work done by non-conservative forces. So let's have a look at a couple of examples now. One where we'll consider a case with no friction, and then we'll consider a case with friction and see how we can use the energy approach to solve these problems. So first we'll attempt a question without friction. A 0.500 kilogram cart rolls up a ramp with an initial speed of 3.00 meters per second. The ramp makes an angle of 20 degrees with the horizontal. Assume friction is negligible. How far along the ramp does the cart roll before coming to rest? Part 2. What speed does the cart have when it returns to its starting position? Okay, so with part 1, we're going to be using our law of conservation of mechanical energy, as we can assume that friction, which is the only non-conservative force that could possibly apply in this case, is negligible. So we have that the initial potential plus the initial kinetic energy is equal to the final potential plus the final kinetic energy, as E remains constant. Now we can say that initially at some height 0, we can say U initial is equal to 0, and then up here we've got U final, and this is at height h, and this is an angle theta in here, and we're trying to find out how far along the slope it's rolled. So we'll call the distance it's rolled along the slope L. So then you can see with trigonometry we've got sine theta is equal to opposite, which is the height h, over the hypotenuse, which is how far it's gone, L. So we can write, well, h is equal to L sine theta. So this tells you the height of the cart when it's rolled some distance L. And at the end of its rolling, it's not going to be moving, so the final kinetic energy is also going to be 0. So what we've got is that the initial kinetic energy is equal to the final potential energy. So substituting in, we've got a half mv squared is equal to, sorry, that should be u. We'll use u to stand for the initial speed. So this is the 3 meters per second. And u, that's equal to mg h. So m is a common factor on each side, so it cancels out. We could have at this point put in numbers, but it's a bit neater if we simplify it algebraically before substituting in the numbers. So that's why I'm doing it this way. And then h we've said is equal to L sine theta. So this is GL sine theta. And what we've been asked to find is how far along the slope it goes. So what we're looking for is L. So we can rearrange this, and we've got L is equal to u squared over 2g sine theta, which is now as simplified as we can get it. So we're now ready to substitute in our numbers. So the initial speed, that was 3 meters per second. So that's 3 squared over 2 times g, which is 9.8 times sine of 20. And solving that on the calculator, we end up with 1.34 meters, which is equal to 1.3 meters. And that's to 2 sig fig, as the 20 degrees was given to two significant figures. Now, part 2 says, what speed does the cart have when it returns to its starting position? So our cart is going to go up to some point at which its final speed will be 0, and then it's going to roll back down. Now, throughout this process, non-conservative forces are doing no work, so energy is conserved, which tells us that the initial kinetic energy is equal to the final kinetic energy as it returns to its position here where the u is equal to 0. And so if the initial kinetic energy is the same as the final kinetic energy, the mass of the cart has not changed. So this tells us that V final is equal to V initial, so that's equal to 3 meters per second. So it's going at 3 meters per second when it returns to its initial position. Now let's consider an example with friction. A 0.500 kilogram box slides up a ramp with an initial speed of 3.00 meters per second. The ramp makes an angle of 20.0 degrees with the horizontal. The coefficients of friction between the box and the slope are mu k equals 0.200 and mu s equals 0.250. Part 1. How far along the ramp does the box slide before coming to rest? And part 2. What speed does the box have when it returns to its starting position? So hopefully this question is a bit familiar to you because we did look at this exact same question when we were considering forces. So we're going to show now how we can solve the same question using an energy approach. Okay, so let's draw a little diagram here. Here's our slope. This is at an angle theta is equal to 20 degrees. We're considering it going up. Let's call it some distance L because it's asked us to find how far along the ramp it slides. So we're finding L, and we've got the height here, the height that it gets to. So using trigonometry, we know that sine theta is equal to h over L, which tells us that h is equal to L sine theta. So with our energy considerations, we've got that the initial energy is equal to the final energy plus the work done against the non-conservative forces, which is friction in this case. So the work done in this case is equal to L times the frictional force, and this is removing the energy from the system. So we've got that our initial energy, initially all the energy is in the form of kinetic energy. It's got no potential energy. So EI is equal to UI plus KI, but UI is 0. So this is equal to a half mu squared is equal to the final energy. Now, when it comes to rest, it's at rest, so it's got no speed, so it's got no kinetic energy. So this will be potential energy, so in the form of gravitational potential energy. So that's mgh plus the work done overcoming friction, which is equal to L times the frictional force. And the frictional force, in this case it's moving, so it's got kinetic friction, so it's mu k times the normal force, and the normal force is equal to mg cos theta. So this is plus L times mu k mg cos theta. Okay, and so let's substitute in for h here. H is equal to L sine theta. So we've got mg L sine theta plus L mu k mg cos theta. And that's equal to a half mu squared. So m is a common factor. So let's cancel it out. And we can pull L out as a common factor on this side. So we've got, well, we can actually pull out Lg times sine theta plus mu k cos theta. And so rearranging this, we end up with L is equal to u squared over 2g sine theta plus mu k cos theta, at which point we've simplified it as much as we can, so we're ready to substitute in our variables. So u, the initial speed, that's 3 squared over 2 times 9.80 times sine of 20 plus mu k, which was 0.200, times cos of 20. And solving this on the calculator, we end up with 0.866 meters, which, if you look back at how we solved it for the forces case, we ended up with exactly the same number there, which is what we expect. Both these methods should work. Now, part 2, what speed does the box have when it returns to its starting position? So once again, we're going to use this rule of conservation of energy, only in this case our finishing and starting positions are the same place, and they're here at the bottom of the slope. So in this case, we've got that the initial kinetic energy plus the initial potential energy, which is 0, is equal to the final kinetic energy plus the final potential energy, which again is 0 because it's back to the bottom, plus the work done against friction. So we've got a half mu squared is equal to a half mv squared, where v is standing for the final velocity, plus the work done against friction. Now the box goes up and the box comes back down, and we've calculated here in part 1 how far up the slope it's gone. So as it's going up the slope, it does work against friction, which is given by L times the frictional force, which is the mu k mg cos theta. And then it does that same work against friction as it comes back down. So we've got mu k mg cos theta. So this is the work done against friction going up, the work done against friction coming down. Okay, so let's cancel out our m's. And then what we'll do is we'll multiply both sides by 2. So we end up with u squared is equal to v squared. Now these terms are identical and there's 2 of them. So when we add them together, we end up with 2l mu k g cos theta, but then we're multiplying that by 2. So we end up with 4 of them. So we end up with 4 times l mu k g cos theta. Okay, now what we were tasked with doing was calculating the final velocity. So we can rearrange this. We've got v squared is equal to u squared minus 4l mu k g cos theta. And now we can just substitute in u, that's 3. So this is 3 squared minus 4 times l, which was 0.866. We calculated it, times mu k, which was 0.200, times 9.8 times cos 20, and solving this we end up with 2.62. that's for v squared, and so taking the square root we end up with v is equal to 1.62 meters per second, which is what we got last time as well. So both these methods gave us the same answer.